University of Montreal, and he's going to talk something similar to what Anwar Shachib did, but maybe a bit more with machine learning and brings a bit another context to it. Let's see. And please take it away, Alexandre. Can you share your screen?
Yeah,
wonderful.
Can you see?
Can you do a sound check?
Hello, hello. Can you hear me?
Oh, we cannot hear you yet, so that's on our side, I guess. 1 second.
Can you hear me now? Can you hear me now? Maybe right now.
Yes,
can you hear
I
me?
know you can hear him online, but we in our room physically have a harder time sometimes.
Okay.
How times have changed.
How about now? Test. Hello? Maybe no.
Sorry about that. Still working on it. Just we hear that is something coming in, but
Okay.
not on the audio.
Alexandre, can you try saying something again?
Hello, test. Does that work?
No, we don't hear you.
Okay. Settings. I'm not sure if it's my microphone. I hope not.
Wonderful. We hear something. Yes.
Okay, you hear that? Okay, so
Yeah.
we're just gonna stick to
It's
that.
definitely on our side, so don't worry about that. That's hopefully, yeah, didn't that stress.
Okay,
So,
I'm not. Okay.
Wonderful. I think we are ready to go now, also from our side and not just from your side. So, Alexandre, please take it away. Sorry about that.
Okay, thank you very much. I'm glad to be here with kind-minded folk. It's nice to hear some talks about gravitational lensing. Usually I need to motivate a lot what I'm doing, my work. But now I know our talk was really nice, so I think I'm going to use that to go quickly to my slide. So basically, gravitational lensing is this beautiful kind of phenomenon in the sky. So, I mean, this is one of my favorite images. So this is the cosmic horseshoe. It gets its name from basically the characteristic shape of its ring. And these systems, basically, they allow us to do a lot of science. So the lens image, which is usually a source at high redshift, in this case, it's really its shape is really bent, so it's hard to study just from this image. But so gravitational lensing modeling, one of its goals basically is to undo this distortion and allow us maybe to study the source. Obviously, the other thing that's really interesting is maybe studying the mass of the foreground galaxy. So in this case, a red luminous galaxy. It can tell us about the mass of galaxy. It can tell us about dark matter. So there's a lot of things to do. The current, so basically, and so I'm going to skip this slide because everybody kind of understand this, I hope. But you can understand the source as basically being a background or like a candle, and the foreground as lensing, as a lensing like a wine glass, which bends space. Or if you look through the wine glass, you can see this lensing effect, which is really nice. The current state of our knowledge of these systems is basically now we know hundreds to 1,000 of these systems. And one thing that is hard, and especially looking at these systems with high resolution images, is that they come in a very diverse set. So sometimes you have a ring, sometimes you have 4 images. So it's really hard to develop systems or modeling that can account for this large diversity, even for just galaxy gravitational lenses. As you all know, some of them are very important, so I'm just going to skip what I have to say on this, but we can do cosmology also when there's a quasar that's eliminated, and LSST will be a great tool to do cosmology. So I'm gonna but the point I made about the complexity is really kind of illustrated when you look at like the different scales and the different kind of type of gravitational lenses. So on the right, you can see like the James Webb images of a cluster that produce this lensing effect, and this cluster can have thousands of background sources, which appears as like these little arcs. These systems require very careful mass modeling, so often people will go and pick every kind of galaxy and associate some mass to them, and this kind of approach, the freeform or pixelated mass reconstruction, are also applied in this regime. But these kind of very careful analysis are often much simpler in the cases where you have maybe a group of galaxy, like the one in the middle, the smiley gravitational lens, or the one I showed earlier, where you have maybe like one main deflector. And so people have usually not necessarily studied, more like these pixelated or freeform reconstruction, because the assumption has usually been that a few parameters is enough to characterize the mass distribution. But I mean, so my work, we've been like studying and maybe questioning this assumption. So we've been asking the question, well, okay, so if we have these complicated lens image, can we actually learn something more about these mass distribution? Can we actually reconstruct like a full image or any kind of distribution just from the shape of these lens image? You can see here our setup for our simulation. So we've actually collected galaxies images for our background sources that come from the Cosmos survey, HAC images. And we've collected mass distribution from hydrodynamical simulation, cosmological simulation, in this case, IllustrisTNG, to get realistic foreground images. And we've set up some PSF and noise so that we get observations that are similar to what you would get from HAC and soon from GWST. And our goal basically is to go from this lens image to these two things, right? And so basically, as in the previous talk, what was mentioned about lens modeling is that one of the goal is basically to do this inference. And to do that, you first need to set up your parameters, right? So that's like the traditional approach of this thing is, first you need to figure out which parameters are going to be useful to, so you need to reconstruct the main deflector, maybe other things. Then you need to define a prior over these. And usually the inference is done with MCMC. And these approach rely heavily on the first part, right? Because you need to be really smart about the way you set up those parameters. And it's not obvious how you do a very general approach that's going to be able to do very different system, like just these two that I'm showing, where on one you have one main deflector and on the one you have two deflectors. You either need some human intervention or a very smart system that can handle this. So let me just show like what would happen if maybe we have this system that I just already showed, where there is a main deflector and the subhalo. What happened when you first start to, so you don't know, so you have this automated system, and now you're trying to fit a parallel to it. So the thing that happens, so you don't necessarily have like a picture of it, you just have these parameters. And so your system didn't know that it could actually produce maybe like a subhalo here, which has this kind of hole structure in the lensed image. So what it tries to do, because it doesn't have the flexibility in its parameter to model this, it's going to actually change or deflect the source to kind of find the bump. And that's like the best it can do in this case, in a sense of like a chi-squared reconstruction. So because basically you don't have the flexibility to model the subhalo. So what you would need to do in this case is a human would come and say, well, I need to add parameters for the subhalo. And in this case, now the model has the flexibility to run this. And if your inference algorithm is smart enough, it can figure out the position of the subhalo in the mesh, and it can correct this this problem now. And the source kind of looks like the background that we had initially. Our approach is to say, well, okay, so can we actually build a system that is gonna reconstruct these pixelated maps such that we can reconstruct potentially any galaxy system, even these most complicated one, and potentially discover in these systems dark matter subhalos, or maybe things that we didn't know could potentially like explain these lenses. Okay, so right, but this is like a mess because now we have a very degenerate under-constrained problem, right? So we have much more parameters than we have data. So this is high dimensional. So now, and we need to define very good priors over these like images. And this is very hard. Like no simple 2-point function is gonna work. We need priors that encapsulate information about high order terms. So our approach to do this is to say, well, okay, so we're going to do what's called a recurrent inference machine, which is to say we're going to do likelihood-based inference. And this inference is going to be based, there's going to be a network that controls the optimization, right? In this framework, we don't have to set up a prior. The prior is implicit in our data set that was used to train the network. This is a very general approach, meaning that in general, any kind of problem where you want to solve in this way with an optimization loop, where you have parameters and you have a physical model that kind of simulate your data, you can actually stick a neural network in the middle that just take the gradient of this likelihood with respect to your parameters, and maybe the parameters at the previous steps, and kind of loops over like this. This is a recurrent series, or just an optimization like you would do in gradient descent. But unlike gradient descent, where you actually specifically define your optimization function, here you have a neural network that needs to learn this optimization function. Okay, so I'm not going to go in too much detail over this. We have a paper out. It's on the archive. Link in the Zoom if you're interested. Now I'll just go over the result, what this actually looks like in practice over our simulation. So here I've got a system where I have maybe like a spiral galaxy in the background, and maybe a foreground that is relatively simple looking, except maybe there seems to be like two merging galaxies in the middle. And here, basically, our approach is able to reconstruct in very high detail the source. And in this case, the lens is relatively simple, and there's not much constraint into the very central profile. And when you look at the residual, basically you have noise level reconstruction, meaning that here the chi-square difference with the degrees of freedom is 213, and the degrees of freedom are like 16,000. So it's really, really precise. And the same model can do basically these very complex systems. So here's like the two main deflector system. We have 5 images. Again, noise level reconstruction. And finally, and this surprised us, I mean, this is way, way more complicated than we hope even to reconstruct with this approach, but almost something that looks like out of a cluster. And again, we do noise level reconstruction and we reconstruct a complex source. Right, but those are simulations, so maybe they don't convince you. You want to see what this does on real data. So we actually tried it. So this is like over a full test set. So this works over like thousands and thousands of examples where we tested this approach. On a real image where we don't actually know what the background and the foreground is, and maybe like the noise statistics in the image might break our neural network, here we can actually achieve something really, really good, where the source here is a 2.4 redshift, and the lens was long suspected to potentially have structure that is not explained easily by parallel, because traditional methods based on parallel had a lot of trouble reconstructing this image, even with pixelated source reconstruction. And our model basically kind of tells us a bit that this is not actually totally symmetric, like in all its structures. So it's already interesting. And we're able, so we don't achieve the same level of precision yet on this kind of system, but our chi-squared are very close to 1 already. So we're pretty confident that we're doing something right. And another thing that's interesting about our approach is that basically the way it's set up, the neural network doesn't have to learn the physical model. The physical model we've built into a simulator, so we can actually tune like the redshift, the pixel scale, like things that you wouldn't want your network to kind of learn by itself. So we can actually do something like zooming in on the source. Like here, we didn't use all the pixels that we had, so you could basically zoom on the source and get better constraints even on your system. And I want to compare here with the way it was done with traditional approach. So my laptop is going to die. But here you can see what was done with the parallel and the source reconstruction. And you can see that people had a lot of trouble modeling the system with traditional method, as you can see here on the top, compared to our reconstruction. And maybe I'll show another one. This one was done on a lower resolution image of the system by James et al. In 2018. And you can see they identified 4 clumps in a proto-galaxy, and we actually did the same. So our method was able to reconstruct a source that looks very much like what was accepted before. So I hope I convinced you that basically it's possible to basically have your cake and eat it too, like do machine learning, do fast inference, and actually have a method that's super flexible, that's likelihood based, and that makes sense physically, where you can actually tune the physical parameters and still have something. So our system scales with complexity. It scales with the number of images that you might want to reconstruct. And in principle, it's so flexible, it means that we could in principle discover new things that we didn't expect before because we have these images. Okay, so I'm going to stop here. Thank you. Okay.
Is it on now? Oh, yeah. Wonderful. Thank you very much, Alexandre. Are there any questions in the room or on Zoom? We have time for some questions. Let me see for hands on the Zoom. Then I start with one. So very impressive results. You say like you require implicit priors from your training assumptions. How to overcome these priors? Because most likely they're never totally right to what we see on the sky. Is there a way to inform from the lens sample you're analyzing that you can divide out sort of that prior and assumptions that were made, or what is the way forward in that regard?
So it's interesting, actually, the question about the prior, because in some ways it is because the problem of modeling the gravitational lenses is degenerate, and in general under constraint, this prior is required in some level. So you're never going to do the modeling without a prior. Now, in our case, it's implicit in the training data set. So in some ways, it gives flexibility where you might want to retrain the model with a different data set and maybe see if, but obviously that's kind of an expensive way of searching for priors. But in the sense of like traditional modeling, the prior, even though sometimes it's not explicit in the modeling, it's implicit in the parameterization. So you can't really escape this prior. So that's like one point I would say. But the second thing about could like a single system inform basically like inform sufficiently in the network such that we could reconstruct something that's outside the network. And I think basically this reconstruction here kind of hints that our models can use like it generalize well to data that was outside its training sample, and that we can actually learn from it, from this new image. We can actually learn, we can use this information efficiently. So that's what I would say.
Yeah, thank you, Alexandre. Any other questions, comments, clarifications? Also, junior people are very encouraged. If you have like questions, be it basics or whatever, feel free to throw them in. That's the space here. And also for everyone on Zoom and locally here, if you have follow-up questions, please tag people on the Slack channel. Gautam set up some channels, but do reach out, whether these people are presenting remotely or are physically present here. I think there's a lot we can learn. I see Remy has a question.
Yeah, thanks. Super promising. Out of curiosity, I don't see the residuals for the Horseshoe reconstruction. Do you have them?
Yeah, I didn't put them, but yeah, so they're still significant in the sense that, so if you compare here, yeah, the residual are still significant. So we're talking about the chi-squared of 1.3, like a reduced chi-squared. So this is not yet at the point where we would say we've completely modeled the horseshoe. But overall, I mean, so, and I would say the most interesting part is the fact that there is like this little bright spot here. So that's very interesting in itself. And, we're finding that it's the hardest thing to model in this system. And you won't find it here because it requires very precise modeling of the source, actually. Probably like higher resolution than we can do right now. But we're hoping that we can scale this method to potentially be able to do this kind of modeling at this kind of precision.
So great talk, Alexandre. A lot of these image-based techniques tend to be very sensitive to the details of the actual pipeline that produced the images in the first place, and the details of that pipeline, what settings have been used, etc. So do we know if things change in LSST land itself, if the project changes something, we would have to regenerate an entire new training set? Or is there some way you can do domain adaptation potentially to adapt your existing algorithm to whatever the new version of the pipeline is?
So, okay, so in particular LSST, so this approach is not necessarily aimed at like LSST images, more at the follow-ups, high resolution follow-ups, either from I don't know how longer Hubble has, but James Webb for sure. So obviously our approach is, so our training data is mostly tailored to like these telescope systems. But in principle, because the physical model, which we try to build to mimic basically the telescope system, like so Hubble in this case, our physical model was made to simulate Hubble. But in principle, because the neural network doesn't take into account the physics, we can actually change the physical model and the inference will still work. So this is one, I would say, advantage of our method, is that it's not just a function that takes an input and dish out an output. It's actually just an optimizer, so that the physics or the simulation and like these things, they can be tuned and our approach still works.
Great. I see a hand from Xiaosheng Huang on Zoom. Please go ahead.
Hi, very interesting talk. I have a quick question. There's another small arc. So in the orientation that you're showing the horseshoe right now, to the left of the deflector. Have you tried to model that arc as well?
Which one?
If you go back to your title slide where you showed the horseshoe.
Oh, right. Can I go up? Oh, I need to go up. Come on.
Sorry.
Yeah, so this one here, right?
Exactly.
Yeah. So I mean, this is interesting, right? Because this is a second source. at a different redshift. So yeah, this is actually a jet, and we can barely see its counter image here. So no, we actually don't model this one because we're doing one source at a time right now with our framework. So this actually requires either potentially different assumption to do like the two source. What we think we could do is do them separately, like do the inference separately, but maybe yeah. So this is something maybe that we still need to think about, like how to handle like multiple sources, which is going to be interesting because James Webb images already show that because of the different bands that we're looking at these systems, that multiple sources are very common. So yeah, it's gonna be interesting.
Thank you.
Great. Any other last question? Looking at the junior people. If not, let's thank Alexandre again. It's a nice talk. We have a break until